This lecture is, or this presentation is about refactoring, and I will illustrate it with a case study. Again, comes out of Flash because that's the one I know the best. But upfront, I want to tell you what this presentation is about and what it is not about. So what this is about is a methodology for planning the refactoring process. What I am not telling you about are any instructions on detailed process of refactoring, because that is very much project specific, and for our kinds of projects, the scientific projects, there aren't very many tools out there or even tutorials out there that can be very helpful. So you have to devise your refactoring process yourself. What I hope to do with this presentation is to tell you, help you find ways in which you can devise the things that are important to consider when you're devising your refactoring process, and how you can go about creating a process for yourself with an example, of course. So the things that I will focus on are considerations before and after refactoring, how to develop a workable process, and possible pitfalls and workarounds. Okay. The definition, we have skirted around the definition a little bit, both Jared and I, but it's time to put it down in words. So as defined by the software engineering community, refactoring is applies to object-oriented software where the internals of the implementation are cleaned up without changing the behavior. We definitely are not using this. This presentation is definitely not talking about refactoring in that strict sense at all. In the context of this lecture, this is a broad interpretation where any part of software may change while retaining or enhancing its basic capabilities. And the reason why we have been making use of this is in the context of HPC scientific software. The degree of change is motivated by many factors, and not least of which is the change in platform, and of course the better understanding and therefore higher model fidelity, and therefore a need to refine some implementation, et cetera. And so it may include redesign at a higher level sometimes, the process of making the change for a particular platform. Okay, so if there is any purist here about the use of term refactoring, my apologies ahead, but this is what I mean when I'm talking about refactoring. So before we start on the process of refactoring, the things that we have to consider. It's extremely important to know why you are refactoring. Whether you're refactoring because you need to have a more modular code that you want to make extensible. You want to know whether this refactoring is necessary at all, because usually in codes it's a lot of work, and so you should really consider whether you want to refactor. How deep a change do you want, and how much of the code is going to be affected by this process? But equally important are things like estimating the cost of refactoring. Because that's what ends up happening, and why the software projects tend to run larger, is certain of the important costs, such as the cost of verification, the cost of test development, et cetera, are not taken into account. In case of refactoring, an additional cost is important. It's not, in addition to the expected developer time to do the refactoring and the testing, et cetera, in all probability, this process of refactoring is going to be disrupting the production schedule of the science runs, and the cost of that should be factored in before the start of the process. It's also extremely important to get a buy-in from the stakeholders, and the stakeholders here are the users that are using the code to do the science, and they should be prepared for the time that it takes, as well as for their disruptions, because without that buy-in, things can go very much south. And my example that I am from the case study will illustrate this point in more detail. So the good reasons for refactoring. The biggest one is, of course, the change in platforms. The platform architecture is the driver behind refactoring that is going on in many codes in the high performance computing world these days. Such a change happened once before, so very similar large scale change happened once before when the architecture shifted from the vector architecture to Risc architecture. In vector architectures, the preferred mode of operation was very large vectors on which you just repeated the same operation over and over again, because the efficiency was achieved by repetition of that. The entire architecture was such that the function units were replicated so that multiple functional units were operating in parallel, and then the individual operation units were sort of pipelined. So it was the only efficient way, and in addition to the functional units in the vector machines, the memory was also organized so that you had memory banks, and access to different memory banks did not interfere with one another. So you could do a parallel fetch, and you could pass this whole data through these functional units, and you could get your the parallelization was realized in this way. Then along came the Risc processors with their memory hierarchy, where actually the data locality and the temporal locality of data within the operations was the more desirable way of achieving performance. And so what became useful was a smaller subset of data that you brought into the cache in the system, and then you kept reusing it. So that was the primary change, so that it went from a flat memory model to a hierarchical memory model, where you wanted to keep the data as much as possible in cache. And the interleaved data access that the vector processors had encouraged was exactly the wrong kind of data access pattern for the Risc architectures, right? And then from there we have now gone to the heterogeneous, because from having few CPUs with sufficient memory per CPU, now we are going to several coexisting memory models where we have many cores plus accelerators, and the memory mapping different between the accelerators and the cores. Then there being coherence domains. You would have heard about those earlier during the week, is that when you have many cores, the cache coherency is not maintained across the entire node, that you have subsets of processes across which the cache coherency would be maintained, and so on. And so it is important to note that the reason for making the changes is not that the code will not run on the new machines. The code will still run. What it will not do is it will run in any reasonable amount of time and get you any kind of reasonable performance. So it may very well happen that if you take the code that is designed for the distributed memory model machine of today, and you run it on the exascale platform, it will take longer to get you to the same point that your simulation can get to you now. It's the performance which you will not have, not the correctness. Okay. Then there are other reasons for refactoring, such as if the code was being used as a research prototype, and then the group that was developing it decided to turn it into a production code, in which case it has to undergo certain modularization and so on. It can be, as it has been in the case of Flash, imposing architecture and maintainability on an old code, where there can be significant change in the code base. It can be change in modular discretization or changes in numerical algorithms. If there is a significant change in the intended use for code, for example, if the code was used for one domain that was using its solver in one way, and then another domain thought, oh, you have about half of the solvers I need, why don't I build upon your code instead of trying to start from scratch, and then they may want to refactor in order to enable some of their own capabilities. And then another one is enabling extensibility or configurability within the code, where you might want to have partial common functionality among different usage models, model refinement, etc., etc. Scope of refactoring. So it's important to know before you start the process of refactoring where you want the end product to be. So you want, for performance, you want to know the target improvement, whether you want, if your code is running currently at X% of peak performance of the machine, do you want at the end of refactoring for the next generation of machines, do you still want it to be X%, or you are going to be satisfied with something below X% if that if the change in architecture is sufficient that it's going to give you other advantages, and the degree of change that might be involved to get that same X% of the performance, because it is extremely easy to go down the rabbit hole of squeezing the last little bit of performance, and many people like to do it. And if you are working with a small code, of course it's the best thing to do. But we are talking about codes, as I mentioned in the morning, the ones whose life cycle runs several times the life cycle of the machine. And so you have to be pragmatic about the changes that, and the level of changes you want to do. For maintainability, you want to know the boundaries for imposing structure, because you never want to rewrite the entire code, at least not one shot. If you want to rewrite code, you want to do it in stages, which means that your refactoring stages, it should not be a single refactor, but it should be staged refactor. For example, you might want to ask yourself, am I changing at high enough level that kernels that are implementing the equations, the solvers for the equations, can they be left alone? Or do they also need to change? And if they also need to change, can their change be kept separate from the change to the overall structure of the code, and so on. For extensibility, the questions are same as similar to maintainability with greater emphasis on interfaces and encapsulation. So here is an example of performance-based refactoring from vector machines. So as I said before, for vector processes, the data structures needed to be long vectors. The longer the vector, the better performance it was going to be. So the spatial or temporal locality had no importance, and the way they operated was you get a vector, you perform the first operator on it, you apply the second operator, the third operator, fourth operator, and at the end of it you have your result, and all of this is going in like a chained fashion across the machine. And as I said, there was interleaving memory banks for better performance. Then in the Risc processors, what was more desirable was a small chunk that could fit in the cache, and all four operators ideally could be applied to that bit of memory before you, that bit of data before you threw the data out of cache. Because the memory had hierarchy, and the closer the memory was, the faster access it had, but it was also smaller. And so the small working sets that could persist in closest memory were preferable, and that made the spatial and temporal locality important. So the data structures that enable formation of small working sets were better. And this is an example of an FFT calculation. So in a FFT calculation, you have the basic computation unit is this butterfly, which is you have the input x0 and x1, and there is the multiplication factor omega these are the equations using which you compute the butterflies. And so if you have n data, then you have log n stages of these butterflies where their distance, where their structure keeps changing in the way that's described here in this figure. So obviously in vector operations, the idea would be to have this entire vector go through these operations, and the way they would look like is something like these equations, where you would have the coefficients, the intermediate results obtained by applying one butterfly in one stage, then every time you would do some permutations and then apply these calculations again, where output from one stage becomes the input for the next stage, and it's just the permutations of the omegas that keeps changing all along. And so here, so that was the vector calculation. For the Risc calculation, what changes is that instead of applying the butterfly of one stage to all of the data points that you have at the beginning, what you do is you pick a collection, a subset of data, and you do a set of k butterflies at a time. So there's a blocking of input vector where the first log 2k plus 1 stages are computed in one block, so that so when you start to work on it, all of these 2 stages will be completed before the data is thrown out, and this set of butterflies is then operated on, and then shuffle happens so that the next log 2k plus 1 stages can be computed, and this is repeated until done. So the change that happened was that instead of working with a long data vector, now we are working with blocking of data, and that was the change that made the algorithm go from being good for a vector processor to a Risc machine, right? So the things that happened was that order of operations changed, the loops needed rearranging, and extra nesting in loops happened. And again, the vector algorithm would still have worked, but would have been slower. So that's the kind of challenge we come up against when we are thinking about refactoring as to where. So here, the extent of change was not the butterfly itself, not the speed of butterfly itself, but the organization of the calculation that resulted in doing the appropriate change, and knowing that upfront is important. Planning and implementation. So one of the first things that needs to be done is the cost estimation, because not having a good cost estimation is the biggest pitfall. It changes the level of disruption that you may have in your science production. However, when you have a really large project, the process of doing a cost estimation can be a very costly process in its own right. And because of that, and because of not understanding the extent of change, most projects really do a terrible job of estimation, because people may have a wrong impression about the complexity of the code, or they may not provide enough, they may not provision enough resources for verification and obstacles that may come out. And therefore, refactoring, because of these reasons, often overruns in both time and budget. So the things that can help in this, thank you very much. I really need it. So the factors that can help are knowing the scope and sticking to it, which means that if for some reason during the process of refactoring you find that you need to have a change in scope, then you should re-estimate the cost attached to it. One should plan for all stages with some contingency factors built in, because they are going to happen. It's a given that they are going to happen. There is no one who is ever able to plan a large-scale refactoring without having unexpected things happen. It's absolutely essential to make provision for developing tests and other forms of verification. It is very much possible that the effort required to develop the tests and verification regime is as much work as the code itself. In fact, Jared will attest to the fact that in the process of changing over from moving from Flash 4 to Flash 5, the development of tests initially took a much longer time than the actual code modifications, right? Right. Because if you have insufficient verification in place, then you will incur technical debt, and it will be that much harder later to get the code to work right. And again, in the process of going from Flash 4 to Flash 5, in the prototyping stage, we did acquire technical debt that is still being resolved. So, right. So, in cost estimation, the challenges that come when you have a development going on, when some part of some version of the code is also being used for science work, for production, because the possibility of branch divergence is huge. So if you don't keep some sort of a communication channel going between production and development, then the branches will diverge, and having the code reconcile later on is much harder. So you have to have in place policies for code modification in terms of when, how often should you synchronize the two branches, and what would be the cost of synchronization. So you have to do the cost benefit analysis here in terms of if there is a frequent merge, then there is going to be possible frequent disruptions to production, but if you have very infrequent merges, then the possible time to resolve and reconcile the differences may be larger, and so that has to be carefully calibrated. Again, the production disruptions may happen because at times you may need to do code freezes in order to make deeper change to a code, and then there may be resources required for quick resolution of merge issues. And in this is where the buy-in from the stakeholders is critical, because if stakeholders are not prepared to freeze code when you need to, then the problem can become much more challenging than it has to be. And then the next thing that you have to think about is the on-ramp plan, because you do not ever want to have the change happen all the way from one end to the other. So if you're doing, like, assume that this whole thing was the code and you had a few little bits that you knew needed to be changed and not the rest of the code, then you could perhaps do the change all at once and still come out okay. But if you need to do the entire code all at once, then that is definitely a bad idea. Okay, that's where you have to have an on-ramp plan. So what kind of on-ramp plan can be there? So assume that you're starting from this point where you have a code with one structure. Sorry, this bottom is the code, and so what you can do is you can create the framework or infrastructure in which you are going to move various components from the existing code to the new code. So this can proceed in this way. You should do incrementally, where you take the small component, verify individually, and then migrate it back into the code. So first component goes, the second component goes, the third component goes, and the fourth component goes. That's one way of doing it. Another way of doing it is to alternatively migrating them into a new infrastructure. So you build a new infrastructure, and then you can bring in the bits of codes into the new infrastructure, and that's how you complete the code. So one of them is that you start out, so the first one was you start out with the code, you take individual pieces out, you verify them, and then you migrate them back into the code as before, so that the next doesn't disrupt. If your changes are much deeper at the infrastructural level, then you generate the infrastructure separately, test it, satisfy yourself that that infrastructure is fine, and then you move capabilities one capability at a time into the new infrastructure. Verification is a very critical factor of refactoring. So you should understand the verification needs during the transition right up front, which means that you should have a clear map of where your code are and where your code needs to be in your head, and you should know your error bounds, because in this instance, when you're doing the refactoring, bitwise reproduction is nearly impossible to obtain. So you need to know whether you do it through knowing error bounds, or you do it through having alternative diagnostics like the conservation of physical quantities, etc. You should have a plan. You should, before you start the first bit of code that you want to change, you want to test for code coverage. You want to satisfy yourself that you're not going to inadvertently introduce bugs that will not be caught by the available tests that you have. If you notice gaps, then you should develop new tests before you start the refactoring process. And you should make sure that the tests exist at different granularities, because you want to be able to do this permutation of tests in order to pinpoint the cause of error, as in the matrix that I talked about in my earlier talk. And then there should definitely be demanding integration and system level tests in place. Implementation stage, there should be procedures and policies in place. The developers should know what the end code should be, because they are the ones who are going to be doing the code implementation. There should be policies in place for managing coexistence of production and development, for managing branch divergence, for the policies to determine what, if any, code should be pruned in the process of migrating the code. And this is also very important, because unpruned code, dead code that exists that you do. Refactoring time is a time, an opportunity for you to examine your code to see if there are any dead codes really and get rid of it. Notwithstanding the example I gave where the pruned code turned out not to be the real prunable code, but still there are truly prunable sections of the code that should be eliminated during this phase as much as possible. The policies on schedule of testing, the policies on integration and release, and here by release I mean that it need not be a full release of the software, but even to within internal users, the scientists within the team should have policies on, there should be a policy about releasing it to those internal users as well. So these are the general guidelines, right? Within these guidelines then I'll move over to the example with Flash, which I personally have seen version transitions from 2 to 5. And before me there was a version transition from 1.1 to 2. So, and the history of Flash is very colorful. It covers all types of transitions that you can think of, and so I can't think of a better example to work through to give you a flavor for what refactoring code and can be like. So, Flash's version 1 was basically 3 completely independent codes that had been developed in 3 different groups. One was an adaptive mesh refinement, one was shock hydrodynamics, and one was a collection of degenerate matter equations of state and nuclear burning. They were sort of smashed together and they were told to become one code. Okay, now a few good things happened in that the people who were putting these codes together wanted to use the same code for multiple different types of problems. So they wanted to use them for more than one type of thermonuclear runaway. So they had this idea right from the beginning in their head that they wanted to have composability in the code, and that also motivated them to allow having multiple alternative implementations for the same capability, because for example, in one class of problem, the kind of equation of state you need is completely different from another class of problems, and the nuclear networks that you're burning in different types of supernovae are also completely different. So this notion of multiple alternative implementations was brought in. The challenges here were that all of this was F77 style of programming. There were common blocks all over the place for data sharing. This is, we're talking 1998. So this is a while ago, right? And obviously, because they came from 3 completely different groups, the divergent data structures were not consistent. The coding practices were all over the place. In fact, there were no articulated coding practices in there. So the solution was here that at first they decided not to change the kernels at all. Instead, what they did was they created a setup script and config files. Now, config files are a key concept that they came up with, and that has persisted with all of Flash, is that this is Flash specific syntax. You could say that this is a domain specific configuration language that is known only to Flash's setup script. What config file does is, this is where all the information about permutability of various Flash components is encoded. So it tells you that I need these state variables. I do need to have these capabilities in order to operate. For example, the hydrodynamics will say I need equation of state and I need grid. Grid is the discretized mesh. Some other capabilities such as nuclear burning will say that I need hydrodynamics and I need equation of state and I need mesh, and so on and so forth. So, and then it will also articulate the units or implementations, alternative implementations of the unit that I will not work with. So if you have a hydrodynamics and a magnetohydrodynamics, they will both say that it can only be one or the other. So I will not work with magnetohydrodynamics. So all of this information is encoded in config file. The setup script parses it, and it recursively goes through all of the units and their config files in order to come up with a consistent self-contained application set which has all the components needed to generate that application. Right? And Because the code was F77 and C++ was not really an option at that time, the object-oriented framework was built on top of this F77-like structure by making use of Unix directory structure, where inheritance and encapsulation to some extent was implemented using the Unix directory structure. And the way they got around the problem was having wrapper layers with interfaces. So they started to have a notion of an API, even though it wasn't formalized yet, but a notion of API using which the various units interacted with one another. But this didn't go far enough because of the common blocks. So in the next iteration of refactoring, so these are staged iterations, refactorings that are happening, because doing it all at once was impossible for more than one reason. One of them was, of course, the complexity of the code. The second one was no one was an expert in software engineering practices, and so they were learning as they went, and they did not want to take on more than they can chew. And this was getting done by the domain scientists. So they were really much more motivated to run the code to do their science, but they saw the necessity and they were doing it, but they didn't want to devote all their time to just doing this. So they were taking it in small steps at a time. In version 2, the one thing that they decided to do was to inventory the data, because one of the most confusing things about the code at this point was they didn't know which unit, because of the common block, as to which unit ought to be, or even what data existed. So they, at that time, this is around 2000, the state-of-the-art practice in software architecture design was to have a centralized database. It turned out to be a bad idea for many reasons, but at that time, that was the thing that was happening in codes. So you picked up all data from anywhere. So you basically picked up all of these common blocks, put them in this one common database, and anybody that needed to use that data would query that database. So what happened was, in the process of moving this data, because someone had to touch every bit of data, it was totally inventoried. They were able to classify what kind of data structures were used for what purposes and so on. And so the common blocks were eliminated and interfaces were formalized. So it met the data objective, but that got in the way of modularization, and it also did not allow for any sort of data scoping or partial encapsulation. And the database query overheads made the code very ugly, because every routine that started at every function first had, so they had put strings. Very soon they found, and the string, in order to match the entry, that was the key through which the database was accessed. Very early on in the process, they realized that that was a killer for performance. So the whole thing changed. And here was an example of not understanding the scope of problem initially, and therefore having to change the way these things were carried on. So then what they did was they created a whole bunch of functions that would translate the keys to an integer. And so the first thing that any function did was it made a whole bunch of calls to change their keys to integers, so that for actually getting the data from the database, they could use the integers instead of the strings. The code became very ugly, because right up front you had a whole bunch of these queries before you even got to the first executable statement, truly executable statement. So here, so the reason why there was only partial success was the scope was not fully determined ahead of time. The other thing that happened was that backward compatibility was enforced upon them, and they did not, no one understood the extra strain it was going to put on the developers to have backward compatibility maintained at all time. Because what that did was it precluded needed deep changes, and it hugely increased the developer effort. And it got to a point where for any new developer coming in, there was a very high barrier to entry. So I came into the Flash at the time that the transition to version 2 was partially done. And I can tell you that it was 4 months of navigating my way into the code before I had courage to do my first check-in. And at that time we were not working with distributed version control systems, so it was a centralized CVS system. So it was, if I checked something in, I was going to break the code. And so for a very long time, I just kept doing the development on my own local copy, and it was 4 months before I made a commit. And this too on a completely isolated area. So that was the kind of barrier to entry for a new developer that was there. And there were many reasons for it. The first one was that there wasn't enough buy-in even from the local users. And this goes back to the point of getting a buy-in from the stakeholders. So because there wasn't enough buy-in from the users, they were not convinced that they wanted to have it done in this way, because at this point in time, a few software engineers and developers had been employed, and they were given the task of transitioning the code from version 1 to version 2. And so the scientists were at the same time keeping on adding capabilities while these developers were trying to enforce some kind of a structure on top of the code. And so the Flash 1.6 development continued, and this made things even more complicated, and basically just blew up the cost of doing the transition, because now there was furious development happening in Flash 1.6, and the developers who were working on Flash 2.2, in addition to making sure that they had backward compatibility with 1.6, so they had to do this two-way work, in the sense that they had to make sure that the new capabilities being added to 1.6 are coming into Flash 2, and that they remained compatible with both of the architectures, and that just made the whole process extremely expensive. It was, so Flash 2 was released, and it was a year and a half after the release of Flash 2 that even the internal users of Flash switched over to using Flash 2 for their simulations. They just continued on with Flash 1.6. Even though they both had similar capabilities, because they just were more used to 1.6, and they just kept working with it over and over. So then version 3, which is actually the current architecture, and because version 5 is still a work in progress, and version 4 did not have a deep architectural change at all. So in version 3, now the idea was to make it an extensible code, because even in version 2, it was very difficult to add a new capability to the code, because every time you wanted to add a new capability to the code, it had to go in two different places, one where all of the functionality was, and all of the data that you wanted associated with it, you have to dump it into the centralized database. And so encapsulation was extremely difficult, and because there was no control over the scoping of the data, anyone could modify the data, and that led to many problems, many bugs in the code that had generally made it a headache to do. So another another refactoring was undertaken, version 3, and this time a few lessons learned from version 2 had been applied. The first one was that the stakeholders were, the scientists in the center were brought in, and they were convinced that this had to be a part, and any deep change that needed to happen in the code, the scientists were consulted, their agreement was obtained, and only then the change was proceeded. And sometimes we had to make the case and had arguments about why that change was necessary, but we would not proceed on making the change unless we had people in it. So the things that happened there was we kept the good things that had happened in version 2 were kept, and that was the inheriting directory structure, the configuration, and the customization from earlier versions. Naming conventions were defined. The directory, because we were using directories for inheritance, now we needed to differentiate between the directory that is there for organizational purpose versus a directory that was being used for namespace, and so that was formalized. The differentiation was done between the API and non-API. The unit architecture for every unit was formalized. Null implementations for the API were placed at the top level, and inheritance was more formalized. So API was defined for each unit, etc. The important thing that happened was data ownership and the scope of data was resolved. And so if a unit that did not own a piece of data had to operate with that piece of data, it had to query the unit that owned it. and the lateral dependencies were resolved with encapsulation. The idea of subunits was introduced because you sometimes wanted to turn off just a subsection of a unit's capability and not the whole unit. And the other important thing that happened, because by this time, this was in 2004-2005 time frame, people were beginning to appreciate the need for unit testing and granular testing, and so we built in the unit test framework right alongside of the code. It still exists today. So the way this version transition was carried out was that the framework was first built in isolation completely, which means that we had the backbone, the mesh, and the APIs for all of the units. We could devise the APIs for all of the units because we had a reference code. So many framework design actually fails because people design an API, but they don't know the kind of science, the kind of physics that the code is going to be working with. And so the APIs are not very well informed, and sometimes they end up having too many capabilities and not have the critical capabilities. Here, because we had a reference code, we knew exactly what kind of functionality would be needed, so we created APIs with null implementation. So I still remember the first test and the first release of Flash 3 was just this backbone with a uniform grid implementation of the grid and just the APIs, and you could compile it and you could run it, right? And then, and the ramp-on was planned where the scope of change was determined ahead of time so that data scoping and arbitration was done. We decided that code was mostly not going to be altered at the kernel level this time around also. And so, and as I said before, the scientists were on board with the change, with the plan. So the ramp-on was the second type of ramp-on process that I talked about earlier, is that we had, we built the infrastructure and we built them with a homegrown uniform grid. This is the first thing that we did was we made sure that the API of the grid unit was such that you could change between a uniform grid and adaptive mesh and in a plug-and-play mode at the time of configuration. So all of the infrastructure also had unit test built for the infrastructure before any physics was brought over, and we started running the automated test suite already on the framework before the first unit was brought over, and this test suite was already running on multiple platforms. Now, multiple platforms and running it in different modes is important because the compilers have different degree of tolerance for deviation from standards of the language, and so some bug is caught by one compiler, another bug is caught by another compiler. So this provides another way of making sure that giving you better confidence in your code if you're running it on multiple platforms. And then we devised a strategy by which we would bring over units into the codes. So the first round of migration of physics units was to work with the most mature units that were not undergoing very many changes at any given time. And so things like hydrodynamics and ideal gas equation of state, et cetera, which had been very rock steady and had been in the code from 1998 itself, were the first units to be migrated. And then what we started to do was then we started to bring in units one by one after with a new application that could be configured. So after the first set of units were brought, the hydrodynamics and ideal gas equation of state, tests such as the Sadov blast that I talked about earlier was introduced into the test suite, and that started running in different configurations. And all of this was running with uniform grid. And then the next thing we did was make it work with the adaptive mesh refinement. And then we started to bring in the units based upon the production applications that were being used by the scientists. So next focus was that they were running the supernova applications, so the physics capabilities that were needed for the supernova applications were prioritized for moving over. So instead of picking up units by how easy they were we started to pick up units based upon, so that the entire simulation campaign could switch over from version 2 to version 3. Another thing, and because the scientists were on board here, they were eager to switch over to the software as soon as to Flash 3 as soon as they could, because there was another reason that all of the bugs that had been reported by internal as well as external users had been listed and had been getting fixed in the process of migration from Flash 2 to Flash 3. So Flash 3 in that sense was far more robust right from the beginning than Flash 3 was. And then, and all along, the scientists were in the loop for verification and prioritizing physics migration. So this was a much more successful refactoring process, at the end of which we had an extensible code with a good code architecture, and that the first release was in 2006, and until 2018, that is now, the same basic architecture has remained. In the time, the code has gone, it was a code designed for the astrophysics community for doing these supernova kind of simulations. In this time, the code has been adopted additionally by the solar physics community, the cosmology community, the star formation community, the fluid structure interactions and biomechanical simulation community, and all because it is possible for these communities to just bring their capabilities, add them, use the infrastructure and some of the solvers that are sitting around, and customize it for their use. Then version 4 was actually a capability building exercise, so it did not need any change in architecture, very, very few structural changes, and no or minimal changes to the existing code. So this was a name version change because there was the physics capabilities in the code roughly doubled, and that's why it became a new version. And now we are undergoing another major, and so there was no need for an explicit version transition methodology. Now we are doing yet another refactor. This is necessitated by the increasing heterogeneity in the platform architecture. There is no other reason to do it. It is just that the current incarnation of Flash's architecture has become inefficient to use on the new heterogeneous architectures. And so it needs another refactoring. So now the objective is to prepare it for platform deeper heterogeneity, because we are looking at hierarchical parallelism in the platforms. We are looking at the billion-way parallelism, which makes the bulk synchronous. So currently, most of the distributed memory machines, codes designed for distributed memory machines operated in this bulk synchronous mode, where you did a bunch of things separately for a while, and then you had a synchronization step where you did data exchange with one another and you carried on. What it did was it made it easy to resolve dependencies. It's not that those synchronization points are really needed in these codes. It is that you don't have to articulate dependencies very explicitly, because that is a very easy way of resolving. And because those points were fewer, you did a lot of calculations between the two different points of synchronization. The overheads weren't too many, and so that was generally a useful strategy to have. Now that there is a great deal of parallelism within the node, and those kinds of synchronous points have now become an actual performance problem, and so we have to move away from this bulk synchronous mode, because we also within the node, different computation units will be operating at different speeds, and so you cannot expect them to work in lockstep even if you divide up the work consistently between them. And then there are different targets for execution, because you can have a CPU, you can have an accelerator, you can have different types of accelerators, you can even have FPGAs hanging off of them, and so on. So the things that are needed in the code in order to enable it to work well with this, these changes in platform is we need a deeper encapsulation of physics kernel, so that knowledge of grid is further abstracted from the code. And we need to constrain the semantics so that the code transformation can happen for optimization, so that the same code that is written once can be executed on different heterogeneous target architecture, target platforms. So, the approach is to determine the level of modifications for each aspect of change in code. There were two aspects, right? The one is to do with actually there are three. So, one of them has to do with hierarchical parallelism, the second one has to do with asynchronous execution, and the third one has to do with heterogeneous targets, right? So, in order to do that, so the way we devise this is to keep wherever possible, to keep these modifications orthogonal between different aspects, which means that the modifications that need to happen for hierarchical parallelism should be orthogonal to the changes that need to happen for asynchronicity, should be orthogonal to the changes that are happening for different target platforms. So we determine changes to setup script, config, and the API, devise an approach to prototyping, devise verification methodology, add tests, and devise an approach for moving from prototyping to production code. So how are we doing this? It turns out that actually the changes required to do the hierarchical parallelism and asynchronicity actually are done using the same method, even and some of this work is getting hidden by Flash itself, by the adaptive mesh package we are going with. So the thing that we do is we change, so in an adaptive mesh usually there is a bunch of blocks and you apply an operator to a block at a time. So there is on every node there is this looping over blocks where you go over all the blocks that are assigned to that particular node. So now the thing that happened is that instead of explicitly looping over these blocks, now we are using smart iterators. So the changes in the Flash physics units is the biggest change is this change in how the looping over blocks happens with smart iterators. These iterators also carry with them all of the meta information that is required for the block. So for example, the extent of the block, the DT attached with the block, etc., anything that might be needed by the physics kernel is actually carried along with these smart iterators. Under the hood, AMRX, the new AMR package that Flash is going to be working with, actually can give you not only just, it does a few things. It can subdivide a block further in order to incorporate higher hierarchy in parallelism. And instead of giving an entire block at a time, it can give a subset of a block, which we usually refer to as a tile, to the iterator at a time. As far as the physics operator in Flash is concerned, it cannot tell the difference between a tile and a block. So it will happily take a tile and it will operate on that. Additionally, because the physics is not explicitly asking for a specific block, under the hood, AMRX can also implement asynchronicity, where it can say if whichever blocks dependencies have been met, it can give that block to Flash to operate on. Okay. So that's how those two things can happen, and at the level of Flash, we are only changing the way in which we are looping over blocks and the way we are obtaining meta information about the block in order to do the calculations. The second part is that we are taking the kernel implementations, and wherever possible we are replacing bunches of lines of code with function calls. Usually you don't want to do that because there is the overhead of function call. So if you, for example, insert a function and a triply nested loop, the overhead of that function call is going to be so bad that you're going to be performing really, really badly. And this is where things like code transformation come in, is that we are working with a team that is developing a tool whereby wherever we have put in a function call, they will just simply replace it with an inline code. So after the code transformation, the code is going to look like this humongous, huge, big code, but the code that we are maintaining is a much smaller code, and because of that, they can generate the code for through this code translation process, they can generate code that is meant for different target architectures. So in this way, we've also succeeded in orthogonalizing the two types of development that need to happen, because one type of development doesn't need to touch the other, and they do not interfere with one another. So to summarize, To have good outcome from refactoring, you should know why, you should know how much, you should know the cost, you should plan, you should have strong testing and verification, and you should get a buy-in from the stakeholders. That's the end of lectures for today.